Evening, class. Yes, I want us to start. Just confirm to me that's visible. Thank you very much. So today we are going to start by discussing what we call Markov and Chebyshev or Chebyshev inequalities. Uh, and these inequalities are very important in probability theory, more so in the study of the law of large numbers in random samples. And this concept is applicable to any random variable, be it discrete or continuous. So it does not depend on a particular distribution. So this is a concept which which is true generally with respect to any random variable, be it discrete or continuous. So it does not depend on a particular distribution. So these inequalities are very useful in the study of the law of large numbers, which we in random samples, which we shall consider later on. So we shall start with what we call Markov inequality. This is named after the Russian mathematician called A. Markov. So let probability that a random variable x is greater or equals 0, pu equals to 1. So the meaning of this, we are actually saying the random variable x is non-negative. So we are dealing here with a random variable which does not take negative values. Then for any given epsilon greater than 0, or put it another way, an arbitrary positive real number, which we are calling epsilon, the probability that the random variable x is greater or equals to epsilon, that means that positive real number, will always be less or equals to expected of x over epsilon. So we are considering a non-negative random variable, and given any arbitrary positive real number, the probability that a random variable x is greater or equals to that epsilon will always be less or equals to expected of x over epsilon. Or put in other words, the mean of x over epsilon. So this is well defined because epsilon is greater than 0. So we are going to prove it. So we suppose that x is discrete. In fact, when x is continuous, we have a similar proof, only that summation or integral replaces summation when x is continuous. So in our proof, let us suppose that x is discrete. Suppose that x is discrete. Then for any given number epsilon, expected of x, this by definition of expectation of x is actually by definition of expectation of x. We are defining expectation of x, that is actually by definition or basically from first principles. So this is the lowercase x, remember the notation, the value assumed by the random variable. So you multiply the value assumed by the random variable by the probability that the random variable takes the value x, and then you sum over possible values of x. Now we want to decompose this sum into two components where in one part x is less than epsilon, and in one part x is greater or equals to epsilon. So you can see this part I've said we are summing for x when x is less than epsilon and here x is greater or equals to epsilon. So we have just decomposed into two components. And remember, the components on the right-hand side are both non-negative. So this part is non-negative, this part is non-negative. So we have two components, we're summing two components that are non-negative. Then definitely the sum of two components which are both non-negative will always be greater or equal to the second component. That is plausible. So that's the sum of the two components will always be greater or equal to the second component. So equality will be valid if this part is zero. That they'll be equal. Otherwise, the sum of the two components, which is actually the expectation of x, will always be greater or equal to that second component. Now, again, we have said we are summing over x when x is greater or equal to epsilon. So this summation also will be greater or equal to this summation because x is greater or equals to epsilon. So you see, I'm summing here. If you replace x here by epsilon, then this summation will always be greater or equal to this summation because x is greater or equal to epsilon. But epsilon is a constant, so it can get outside the summation. So this epsilon is a constant can get outside the summation. So I'm actually summing now probabilities whenever x is greater or equal to epsilon. So this event, so you have an event where x equals to x, and then you sum all probabilities whenever x is greater or equals to epsilon. So it will actually give us the probability that the random variable x takes values which are greater or equals to epsilon. So we are actually saying now a spread of x will be greater or equals to epsilon times probability that x is greater or equals to epsilon. Make the probability the subject. Take this to the left-hand side. So we are basically saying probability that x greater or equals to epsilon will be less or equals to a spread of x over epsilon, which we are actually proving. That is now the Markov inequality. That is now the Markov. So the only assumption we are making here is that we are dealing with a non-negative random variable. No other assumptions. And of course, we are dealing also with a positive real number epsilon. So we really don't have to prove for continuous x, because when x is continuous, we don't sum, we integrate. So wherever you see a summation to be replaced by an integral, and we shall have the same result. So for continuous x, we can simply say integral replaces summation, and we are done. Now, we can have also Markov in a more general form. In general, suppose we define or a function of a random variable, and that function is non-negative. Suppose we define g of x, which is non-negative. Then we can have Markov inequality in terms of that function of the random variable. So if probability of g of x is being greater or equal to 0 is 1, so we are actually saying this g of x is non-negative. The random variable g of x is non-negative, does not take negative values. Then a more general form of the Markov inequality is expressed as follows. Remember also the epsilon is a positive real number. Then we are just saying probability of g of x greater or equals to epsilon is less or equals to expected of g of x over epsilon. So the one we have here is actually the simplest version of Markov inequality when we are dealing with the identity function. When you are dealing with g of x equals to x, that is the identity function. But this is more general version of the Markov inequality. So long as you have a random variable which is non-negative, you can apply Markov. So we are saying also, if we had a random variable and we have defined a function which is non-negative g of x, then we can apply Markov. We have Markov inequality, which is which is actually used in obtaining what you call the Chebyshev inequality. So let us consider Chebyshev. So actually, you'll find that to get the Chebyshev inequality, we actually use Markov. So let us consider Chebyshev's inequality. Let x be a random variable for which power of x is finite. Then for any given number epsilon, which is positive, the probability that the absolute value of the random variable x minus its mean being greater or equal to epsilon will be less or equal to power of x over epsilon squared. I repeat, the probability that the absolute value of the difference between the random variable and its mean or its expected value being greater or equal to epsilon is less or equal to power of x over epsilon squared. This is Chebyshev's inequality. So in the proof, in the proof, we just use our general fashion of Markov, where we take our g of x to be the absolute value of x minus x squared of x. You can see this function, the absolute value cannot be negative, so it is not negative. So our Markov inequality is valid here, so we can apply it. And Markov says, remember the one Markov says, probability that g of x greater or equals to epsilon is less or equals to x squared of g of x over epsilon. So when you apply that, well, this is actually our g of x. Probability that g of x greater or equals to epsilon. But when we say mod of x minus x squared of x greater or equals to epsilon, that event is equivalent to the random variable x minus x squared of x squared greater or equals to epsilon squared. The two events are equivalent, and equivalent events have equal probability. It is like if I say, if mod of x, just for the sake of argument, say you have a number x, say greater or equal to some number a, mod of x greater or equal to some number a, that will actually mean that that number, the x squared, will always be greater or equals to a squared. You can check a few numbers and verify. If mod of x is greater or equals to some number a, then actually x squared will always be greater or equals to a squared. So that's we are saying mod of x minus its mean greater or equals to epsilon is equivalent to x minus its mean square being greater or equals to epsilon squared. So the two events are equivalent, so they will have equal probability. And then here now we apply the Markov inequality. So we are dealing with a non-negative random variable here. And then we have, and then the non-negative random variable is the square. And then we have our number, which is also non-negative, epsilon squared is also non-negative. So Markov says the probability of the square of x minus its mean being greater or equals to epsilon squared will always be less or equals to expectation of the random variable divided by the constant. So the random variable in equation is x minus x squared of x squared. And the constant now, the real number is epsilon squared. So we have applied here Markov. The first inequality, we are just applying equivalence of the two events. And then in the last expression for the inequality here, we are actually applying Markov inequality here. But you can see the numerator here, by definition, expected of x minus its mean squared, by definition, this is actually var of x. And hence the proof. So we can actually put that actually the Chebyshev inequality is a special case of Markov inequality. Mm. Because for Markov, we are just talking of g of x, which is non-negative, but we are pick a particular function of x, which is the mode of x minus x squared of x. So it's exactly a special case of Markov inequality. Now, in its usage, remember our notation, what we said, we shall be using mu to denote the mean of whatever distribution. Also, we shall be using sigma squared to denote variance. So we can actually express our Chebyshev inequality using those notations. We replace square of x by mu, and you replace var of x by sigma squared. So we shall have that Chebyshev inequality as probability of mod of x minus mu being greater than or equal to epsilon would be less or equal to sigma squared over epsilon squared. So also it is in a more compact form and also very easy to remember. It is in a more compact form and very easy to remember. Further, in its usage, suppose we let our epsilon to be a constant, to be, because remember, epsilon is positive, and always standard deviation is taken to be positive. So sigma is also positive. So suppose we say epsilon can be factorized as k sigma. Or in other words, we say uh, epsilon is k times sigma, or it can be factorized as k sigma, so k must also be positive. So sigma is positive, k is positive because epsilon is positive. Then if in this formula now we can replace epsilon by k sigma, we have it in another fashion. We say probability of mod of x minus mu greater or equal to k sigma. Remember, k sigma is our epsilon, would be less or equal to sigma squared over epsilon squared. So remember, so in the numerator, you have sigma squared over epsilon squared, but epsilon squared now is k squared sigma squared. So sigma squares cancel. Then I have 1 over k squared. So we are saying probability that mod of x minus mu being greater or equal to k sigma will always be less or equal to 1 over k squared. We are calling it single star. Or equivalently, using the complementation rule, we can say probability that the mod of x minus mu, remember now here it is greater or equals to, if you reverse the inequality, it becomes less or equals to k sigma. So this understand means we are going to reverse this inequality also. And remember, you are using the rule of complementation. So the probability on the right-hand side should be 1 minus what we have on the right-hand side of star. So the two expressions, so we are saying probability that mod of x minus mu being greater or equals to k sigma is less or equals to 1 over k squared, which is single star, and this equivalent fashion is given by double star, which you have obtained by using complementation rule of probability. So probability that mod of x minus mu being less or equals to k sigma will always be greater or equals to 1 minus 1 over k squared. That is the double star. Now, the interpretations. Inequality star gives us the upper bound of this probability because it actually says less or equals to. So you can see the event in question here. So it is giving us the upper bound of the probability on the left-hand side. So it is gives us the single star, gives us the upper bound of this probability, the probability you have on the left-hand side. While inequality double star gives us the lower bound of the probability we have on the left-hand side. So it is the lower bound in the sense that it says greater or equals to. It means that probability will always be greater or equal to this value. So this is actually the lower bound. It will never, the probability of the left-hand side will never be less than this value. Which when you talk about the one for single star, we are saying the probability of the left-hand side will never be greater than this value. That's why we are talking about the upper bound and the lower bound. So in the question implies the probability of x differing, the physical meaning of this. Inequality star implies the probability of the random variable x differing from its mean. You say mod of x minus mu. Essentially the discrepancy between x and its mean, or the values assumed by the random variable and its mean, the discrepancy. Now, inequality implies the probability of x differing from its mean by more than k standard deviations. This is actually what it means. By more than k standard deviations. This is actually k standard deviations. By more than k standard deviations is less than or equals to 1 over k squared. Equivalently, inequality double star implies the probability that x will lie. You see, this is now, you can see this less or equals to means will lie within k standard deviations of its mean is greater than or equals to 1 minus 1 over k squared. So this is quite remarkable in view of the fact that we have not even specified the probability distribution of the random variable. We have not. So these are general results, really general to any non-negative random variable. Ordinarily, to evaluate the probability of an event described in terms of random variable x, the probability distribution of x is required. The Jeffreys inequality gives us a bound which does not depend on the distribution of x, but the probability of particular events described in terms of a random variable and its mean and variance. So that is so that marks the end of the two inequalities that we have seen. One is a split of the other one. And they are very general. I want to look at moment, what you call moment generating function, a very important function also in probability, because it can be used. Remember one time we talked about moments, and in particular the raw moments. This function can be used to generate the raw moments of a distribution. So once you know the MGF of a distribution, you can actually use it to generate moments instead of getting them from first principles. So as far as this function is concerned, it is also defined for both discrete and continuous random variables. In other words, for both continuous, discrete and continuous probability distributions. So in short, we shall be just calling it MGF, moment generating function. Consider a random variable with probability distribution f of x. This is our usual notation. The moment generating function of x, or simply MGF, is denoted by m of t. So we are actually saying we are denoting the function using the letter m, and this argument is t. So it is m of t. So this is basically the notation. This notation for MGF. And now the next is a definition and defined by. So you can see on the left-hand side, we have our notation denoting the MGF, and then the right-hand side is now giving us its definition. Is expectation of exponent tx. So remember, x is now random. So e raised to tx or exponent tx is a random variable because x is random. So it is a function of a random variable x. So this is a random variable. But here t is not random. It's just a real number. That's why I'm saying t is in R, meaning t is just a real number. So using our knowledge on how to determine expectation, we know how to do that. So for discrete x, you sum up a possible values of x, exponent tx times this probability distribution. So this is exponent tx f of x as before. This expectation of exponent tx. Remember now x here inside the summation should be lowercase. Here should not be put, you should not have it as random because it's the value of the random variable. And then for continuous x, we just integrate. Instead of summing, we integrate over R. So these are the two fashions, depending on whether x is discrete or continuous. But basically, that is just the MGF. So when it exists, the expectation actually depends on the choice of t. That is why we are saying this is a function of t. And so it defines a function of t. For t equals 0, it always exists. Because if you put substitute t equals 0, you are calculating expectation of e raised to 0. And e raised to 0 is 1. So m of 0 is expected of 1, and 1 is a constant. Expectation of a constant is a constant. So m of 0 is always 1. So it always exists at t0. The MGF always exists at t0. But for other values of t, the existence of m of t depends on the distribution. It depends on the distribution itself. Now, for any random variable x, the MGF must exist at the point t equals 0. So if the random variable x is bounded, then m of t exists for all values of t. I believe you understand what we mean by saying a random variable is bounded. If the random variable x is not bounded, then m of t might exist for some values of t and might not exist for others. If the MGF of x exists for all values of t in some interval around the point t0, it can be shown that the derivative of mt, which we are calling now m prime of t, exists at the point t0. So if the MGF of x exists for all values of t in some interval around the point t0, we are saying in the neighborhood of 0, it can be shown that the derivative, which is of mt, which we are calling it m prime of t, exists at the point t0. And at t0, the derivative of the expectation must be equal to the expectation of the derivative. That is an aspect of calculus when it comes to derivatives. So this is basically what we are saying. Thus, this derivative of m of t evaluated at t0 is how we can write. So m prime of 0 is actually the derivative of m of t evaluated at t0. So we are saying differentiate the MGF and evaluate at t0. But the MGF is expected of exponent tx. So you differentiate that with respect to t. And remember the premise which you have said that it can be shown that the derivative exceeds at the point t0, and at this point, the derivative of the expectation must be equal to expectation of the derivative. So when we are talking about derivative of expectation, then we are talking about the expectation of the derivative at that point. The first line talks about derivative of expectation. The second line says expectation of the derivative. So we are using that premise of calculus at that point, which is actually t0. So, so inside expectation now, we find the derivative of exponent tx with respect to t. So you differentiate the power with respect to t, you get x. So x comes, you multiply by x, so e raised to x. So it's a derivative. And then evaluate it at t0. Then you take expectation. If you evaluate this at t0, you are going to get x, because e raised to 0 is 1. And then you get the spread of x. So we have found the mean of x using the MGF. Right? So to get actually the mean of x using the MGF, it says differentiate the MGF and evaluate it at 0, you have the mean. So you can see once you have the MGF, you don't have to get the mean from first principles. So we have obtained the mean of the runoff variable or of the distribution without necessarily using the probability distribution. Of course, we have to take cognizance of the fact that you need the distribution, of course, to get the MGF. You need the distribution to get the MGF. But once you have it, then you can use it to find the mean. In particular, as you shall see in general, we can use it to obtain the raw moments. In fact, the mean is the first raw moment, by the way. Now we can generalize this, that in general, if the MGF M of t of x exists for all values of t in an interval around the point t0, so you can see what is actually required for one to generate moments using MGF, it must exist in the neighborhood of t0. It must exist in the neighborhood of 0. So in general, if the MGF M of t of x exists for all values of t in an interval around the point t equals 0, then it can be shown that all moments expressed of x raised to r is actually the rth raw moment of x must exist. It means that all the raw moments must exist. Furthermore, it can be shown that it is possible to differentiate m of t any arbitrary number of times at the point t equals 0. For instance, the one we have just done was a first derivative, but you are saying we can actually differentiate it an arbitrary number of times. That means you can get the second derivative, you can get the third derivative, and so forth. So in general, because our interest here is to obtain the earth raw moment, then we are going to differentiate, we are going to obtain the earth derivative of MGF. And when we evaluate it at t equals 0, then you will get the earth raw moment. So basically, this is what you are doing here. So we are going to denote the r derivative of MGF evaluated at t0 as m and then superscript r in brackets to denote the order of the derivative and then evaluate it at t0. So basically, you can see now we are going to put here the r derivative, dr dtr. This is the r derivative of mt with respect to t. But this is MGF. So you are saying differentiate this r. You get the first derivative, the second derivative, and so solve the r derivative. So if you do that, if you get the r derivative of e raised to tx, each time we know with the first derivative, you can see x is coming. When you get the second derivative, it becomes x squared. When you get the third derivative, it will become x cubed. So when you get the r derivative, you will get here x raised to r. So the r derivative of exponent tx is x raised to r e exponent tx. So when you evaluate it at t0, e raised to 0 is 1. You get x raised to r. So expectation of x raised to r is actually the rth raw moment. If you recall our notation, We are calling it mu r prime. So this is the earth raw moment. So r is 1, 2, 3, and so forth, depending on the order of the order you want, or which moment you want. So basically, you are actually saying to get the earth raw moment, you evaluate the earth derivative of MGF, and you evaluate it at T0. So the name, so why we have the name moment generating function? It is because it generates these moments. That is why it is called moment generating function. Now, an important aspect of this MGF is that it uniquely determines a distribution. You know, if you and conversely, if the MGF exists, it is unique. So actually, MGF is unique to a distribution. You cannot have two different distributions having the same MGF. Mm. And if the two distributions have the same MGF, then they must be identically the same. That's why we're saying uniquely determines a distribution. And conversely, if the MGF exists, it is unique. There exist some variables for which the MGF does not exist in an interval around the point t equals 0. There exist some variables for which the MGF does not exist in an interval around the point t equals 0. So one of the premises why you are able to generate these raw moments is because the assumption here is that the MGF exists around the point t in an interval around the point t equals to 0. In other words, the neighborhood of 0. It exists in the neighborhood of 0. But I'm saying here there exist some variables for which the MGF does not exist in an interval around the point t equals to 0. And a very good example is this one. I have an example here which I can use to illustrate that. We have this distribution f of x, which is 6 over pi x squared. This x is discrete here. The x the values 1, 2, 3 up to infinity. This distribution is actually related to recall the parcel problem when you are talking about the Riemann zeta function. You remember the Riemann zeta function? When the argument, when you are having summation up to say pi squared over 6, you can check in the notes. Now, if we are to determine the MGF of this distribution, this is how it goes. M of t, x squared of etx. So you get your distribution, you multiply by e raised to tx. Oh, 6 over pi squared is a constant, can get outside. So I'll have e or exponent tx over x squared. I'm summing that. If you have a series whose from x equals to 1 to infinity, whose terms are exponent tx over x squared. Remember, t is real here. When we look at two situations here, suppose t is positive. If t is positive, let us see what will happen to the term of this series. Suppose t is positive. What happens as x increases for the x term of the series? Now we are now using we have to. It says we are in calculus. You also usually learn about series, talk about convergence and divergence of series. And you know that for a series to converge, it is necessary that the terms converge, vanish or converge to 0. But also remember, when the terms of a series converge, it doesn't mean that it will converge. A sufficient condition for a series to converge is that the partial sums of the series must converge. So by definition, we have defined our MGF. Let us see this possible, this situation when t is positive, and then what will happen to the x term of the series. So if I find the limit of the x term of the series as x tends to infinity, what happens? This one you need to use the what you call Hospital's rule, where you differentiate the numerator and the denominator until you either determine whether you'll be able to deduce whether it is converging or not. You use Hopital's rules in situations where you end up with, when you are talking about infinity over infinity, you have to use Hopital's rule. So when you end up with things like 0 over 0, you have to employ Hopital's rule till you decide whether it is converging or not. And you can use it a number of times. So I'm actually applying Hospital's rule here. I'm differentiating the numerator, and then you differentiate the denominator. Remember, with respect to x now, because we are looking for the limit as x tends to infinity. With respect to x. So this is the derivative of numerator, derivative of denominator. If you check again as x tends to infinity, it is still going infinity over infinity. So we have to apply again. Till you say, is it diverging or converging? So when you apply Hopital's rule again, you'll see what will happen here. You'll have t squared e tx. Now the denominator becomes 2. And then you find the limit, oh, it goes to infinity. So the x term goes to infinity. There is no way these series will converge when the terms are not converging and are not even going to 0. So you can see for t equals 0, for this distribution, the MGF does not exist. M of t does not exist when t is 0. Let us see for t less than 0. You can see for t less than 0, the x term will definitely go to 0. Because remember, this t is less than 0. So as x tends to infinity, the numerator goes to 0. So everything goes to 0. So at least we have that necessary condition. The x term is vanishing, is going to 0. And we say the necessary condition for a series to converge is that the term must converge to 0. But that don't mean that when the term converges to 0, the series will converge. A counter example is like the harmonic series. The terms of the harmonic series converge to 0, but the harmonic series diverges. You know, but it's a necessary condition. All series which converge, the terms must converge to 0. Now let us see. So let us see. We can use the techniques of testing convergence. One is what you usually call the comparison test. If you look at this series, the one we are looking at here, summation x equals 1 to infinity of exponent tx over x squared, you can see it's always less than summation over 1 over x squared, so long as when t is less than 0. When t is less than 0, exponent tx will always be less than 1. So meaning this series will always be less than summation over 1 over x squared. And actually the series on the right-hand side converges. You can actually establish that using integral test. This series converges by integral test. You can check in calculus what we mean by integral test. And it actually converges to pi squared over 6. Remember the Parcel problem now. That Parcel problem, I gave you one of the particular cases of the Riemann zeta function. That was evaluated at 2, at s equals 2. We actually saw that this summation is actually equal to pi squared over 6. So when you use integral test, it tells you it converges. It will tell you it converges, yes. But actually, the Parcel problem tells you the actual sum is actually pi squared over 6. Now, because the series in question is less than the series which converges, it means by comparison test, the series on the left, which is the series of interest, will also converge. So we say it also converges by comparison test. In other words, when a series is dominated by a convergent series, the series would converge. Therefore, because we are saying it converges, we are actually saying m of t is finite. We are saying m of t is less than infinity. We are saying m of t is finite. M of t is finite means M of t exists. However, so we have seen that for t greater than 0, MGF does not exist. But for t less than 0, MGF exists. But when we talk about an interval around the point t0, you know, when you talk about the neighborhood of 0, we are talking about to the right and to the left of 0. So it does not exist in the neighborhood of t0. So MGF does not exist in an interval around the point t0. You know? So we cannot actually use even this MGF to generate moments because it does not exist in an interval around the point t equals to 0. In fact, is MGF, in fact, the MGF itself is usually also a very complicated function and still cannot be used to generate moments because of this reason that does not exist around the point t is equal to 0. So to sum it all, so in order to generate moments, these are now in general, MGF must exist in the neighborhood of t equals to 0. Now, in the next section, we are just looking at examples for the basic distributions in probability and the MGFs. The first one is binomial, that is a binomial distribution. We had considered that some time ago. This is how we get the MGF. You shall find the MGF. We have to use here a binomial expansion to get the MGF. And to be sure that your MGF is correct, always evaluate it at T0 and should be 1. If you find it is not 1, then that MGF is not correct because we know all the time M of 0 is always 1. So it is, you use it to check. These things are self-checking. After you have found your MGF, get M of 0 and see whether it is 1. So in this example, this is a binomial that you know the support, the parameter space, MGF by definition. We are using here binomial expansion, and then we have the MGF. And you can see if we evaluate it at T0, we shall have here P plus 1 minus P, you get 1 raised to N. You can see this one, so it's true. You get the first derivative, you must use chain rule. You get the second derivative, you must use chain rule and also the product rule. Because when you have to differentiate this, there is T here and there is T here. So you must use product rule. So this is a first derivative, this is a second derivative. To get the mean, evaluate the first derivative at T0, you get the mean. To get the second moment, evaluate the second derivative at T0, you get that. Then you can now get your variance once you have the moments. Poisson, this is a Poisson distribution. The support 0, 1 up 2 up to infinity. That is the support. The parameter space, positive real. Positive reals. So this is the MGF. Here we have to use the exponential series. You have to know the Maclaurin series of exponential function. So basically we are using here exponential series. You know, exponential series just is the Maclaurin series of exponential function, or simply Taylor series about the origin. So after evaluating, you can see I'm giving you reasons what you can invoke in getting those. You can see I'm talking about binomial expansion. You need to know that. Yeah, now you are supposed to know exponential series. So you come and get your MGF, and if you evaluate at T0, you'll find this one. Differentiate, first derivative, second derivative. Those ones you can follow. You can find the mean, find the second moment, you find the variance. But this is a distribution which has got mean and variance being equal, the Poisson. Usually say Poisson with parameter lambda. Usually when measuring distributions, you have to associate with this parameter. Like when you say binomial with index n and parameter p. We don't say parameters n and p. N is not a parameter, it's an index, the number of Bernoulli experiments performed in order to get binomial. The parameter is only p. And you go Poisson with a parameter lambda, relating to usually what you call a Poisson process. Usually R is what you call the red parameter, which also happens to be the mean. Usually call it the number of occurrences per unit time. Uniform distribution. This is now the continuous case. That's why we call it rectangular. This is a uniform distribution. Which is actually constant over the interval AB. It's given by 1 over B minus A. So you can catch, so you have to integrate because it's continuous. You can see the support is an interval. So you'll have to integrate over the interval AB when getting the MGF. Oh, in fact, I could have this example so that I explain why. Why move 0 here is not 1, and then we shall see why. Why is it not 1? So after integrating exponent tx, and you put the limits, you get this result here. So exponent tp minus exponent ta over t into b minus a. You can see if you put t equals 0, you will have e0 minus e0. That is 1 minus 1, which is 0. And if you put t equals 0, the denominator, you get 0. You can see m of 0 is 0 over 0. And this kind of expression in mathematics, we say it is meaningless. Things called 0 over 0 is meaningless. Even infinity over infinity is also meaningless. But 0 over a finite number is always 0. And a finite number of 0, I'm saying a finite number or 0 over a finite number will always be 0. Or a finite number over infinity will always be 0. But 0 over 0 is meaningless. We usually say it's undefined, or which we usually call it in math is indeterminate. So what it means in mathematics is, so when you get m of 0, you find it indeterminate. It implies that t equals 0 is a singularity. We call it in mathematics a singularity, and it must be removed before differentiating m of t. So when you want to generate moments, and you have found that at t0, the MGF is indeterminate, you don't use it to generate moments. You must remove the singularity before you differentiate. So what do we mean by that? How do we remove the singularity? We actually remove the singularity by division. But essentially what you need to do is to express the exponential function as a series. So you must express the exponential function as a series. You get the exponential series, or basically the Maclaurin expansion of the exponential function. So this is basically what I'm doing. So we have expressed here, we have expressed exponent TB as a series, is this Maclaurin series, minus also exponent TA as a series, is this Maclaurin series. This is a simplification divided by T into B minus A, you end up with this result here. This is the result after now performing the division. So after performing the division, you get the quotient, which is actually your MGF. And if you evaluate now the MGF at T0, you get 1. because you have actually removed the singularity. Meaning, if you have to proceed to find the raw moments of this distribution, we are now going to use the MGF after we have removed the singularity, which is we got the singularity which is t equals 0. You can actually see I'm now using this function m of t after removing the singularity, and then you get the mean, you get the second moment, you differentiate first derivative, second derivative, so you have your mean a plus b over 2, and then you get your variance using the formula. After you simplify, you'll get the variance, which we know. This can be verified from first principles, the way we were doing earlier when you were getting just means and variances. Example number 4, you have what you call the gamma distribution. This is a gamma distribution. They are usually expressed in two types. This is what you call the gamma distribution type 1. So f of x equals to beta raised to alpha x raised to alpha minus 1 exponent minus beta x. And the support is the positive reals. And the parameter space is a subset of R2, actually the first quadrant, because the two parameters, both of them are positive, meaning it is a first quadrant. So to get the MGF, by definition, you integrate over the support 0 to infinity. So ETX, and this is your f of x. So when you substitute that, you get it here. And then for one to integrate this function, this improper integral, I should be having a remark somewhere which will tell you how to deal with it, you know. So to integrate that integral, we use what we call the gamma function. It's gamma of alpha into beta minus t raised to alpha. We have two special functions which you might end up using, in particular the gamma function, also the beta function. And in particular, before even you talk about differentiating to determine the MGF of a gamma function, it ends up requires one to determine this improper integral, which I'm giving the result here. But it is related to what I have here in the remarks. You must have come across what we call the gamma function. The gamma function is one of the special functions. It's actually an improper integral. So the right hand side is actually an improper integral, and it's defined for real or positive alpha. It's defined for positive alpha. So we should denote it. So this improper integral is denoted by what you call the gamma of alpha. That notation is gamma, uppercase gamma, and then it is the function gamma of alpha. We just write it like that. We use brackets when the argument is long. So the gamma of alpha is that improper integral. It's called the gamma function. So if you can see, if you are to integrate the right hand side, you have to use what the integration by parts. I've given you what I mean by that. You have to take one to be u, the other one to be dv dx, and then use integration by parts. After putting the limits, you'll be able to show that gamma of alpha is actually alpha minus 1, gamma of alpha minus 1. So we end up with what you call the recurrence relation, meaning you can use it recursively. You can use it recursively. So always gamma of alpha will always be, you say alpha less 1 times gamma of alpha less 1. So I indicated that when you are writing gamma of alpha, when the argument is long, you can use brackets. Two, in this remark also, you can see that gamma of 1, if I put 1 here, here will become 1. So I'm actually integrating exponent minus x. And this integral is actually 1. So actually, gamma of 1 is 1. In this definition here, we have said alpha is positive number, and you can see basically a real number, which is positive. But suppose we relax that and say, suppose we take positive integers. So if alpha is a positive integer, you will actually find that gamma of alpha, if you are to apply the recurrence relation repeatedly, you will be able to establish that gamma of alpha is actually alpha minus 1 factorial. Alpha minus 1 factorial. And if you are to substitute 1 here, you will actually find gamma of 1 will be 0 factorial. But remark 2 says gamma of 1 is 1. So gamma of 1 is 0 factorial is actually 1. So that's why we usually say 0 factorial is 1. It's through this function. It's actually established through this gamma function that 0 factorial is always 1. Remark number 4, I'm just looking at these remarks because they are very important. It relates to this because this depends in terms of that function, the gamma function. And then how do you come up with this result? So before we really see that, let us look at remark number 4, which we shall be able to use it later. If we consider the standard normal BDF, this is a standard normal BDF. Standard normal in the sense that it has got mean 0 and variance is unity or 1. This is a standard normal BDF. And usually we know that for normal to be symmetric. It is symmetric about its mean, meaning the mean, the median, and the mode coincide at x equals 0, which is the mean. And because now we are dealing with a BDF, if you are to integrate over the support, you should get 1 because it's a BDF. But remember, because it is symmetric, integrating from minus infinity to infinity, and because it is symmetric about x equals 0, I can just say I can integrate from 0 to infinity and I multiply by 2 twice. Because of symmetry, I can say twice from 0 to infinity of the BDF would also be 1. So you symmetry. So if I now want to integrate this, I make a substitution. Y equals to x squared over 2. So that's I'll move from integrating with respect to x to integrating with respect to y. And if you correctly see that y equals to x squared over 2, and x is from 0 to infinity, also y will be from 0 to infinity. So the limits of y are also 0 to infinity. So you require now to get dy dx. So you get your dy. On the right hand side is 2x over 2 dx. So this x dx. And then you need to get your dx. So dx is dy over root 2y. So this dx is actually dy over. So you can see I'm now going to be integrating with respect to my new variable, which is y. And remember, my x squared over 2 here is y. So I have everything in terms of y here now. So this e minus y, e raised to minus y, dy over root of 2y. I have everything in terms of that. I've taken outside the constants, root of 2 pi. So outside I have 2 over root of 2 pi. Now, exponent minus y is here, dy is here. I have here root of y in the denominator. Root of y in the denominator. That means it's actually y raised to a half, and it's in the denominator. If you take it to be the numerator, it will be y raised to minus a half. But y raised to minus a half can be put as y raised to a half minus 1. And if you simplify the constants, you have 2 here, you have root 2 in the denominator, you have root 2 in the denominator, so root 2 and root 2 becomes 2, 2 and 2 cancels. So those constants vanish. So I only remain with 1 over root pi. And when you look at this integral, the one I have here, it is of the form, so you can make, in this integral, multiply through by root pi, multiply through by root of pi. So on the left hand side, I have that improper integral, and the right hand side is root of pi. But if you relate to my remark number 1, look at what the gamma function is. Gamma of alpha is improper integral, which is from 0 to infinity, x raised to alpha minus 1 exponent minus x dx, where alpha is positive. You can see the integral I have here now is actually gamma over half, because where we have alpha here is where our half sits. If you go to remark 1, that means this is gamma over half. So another important expression we have come up with is that gamma over half is root of pi. So these are very important results of the gamma function. 1, gamma of 1 is 1. For positive integer alpha, gamma of alpha is alpha minus 1 factorial. Gamma of a half in particular is actually root of pi. Very, very important. We shall be using them later. Now, 5, remark number 5, will actually lead us to finding this MGF. Why I was giving this result here is a result of remark number 5. And it is related, they are all aspects of the gamma function. So in view of 5, now by making the substitution, y equals to beta x. In this integral, if you go to what you are calling the gamma, look at the gamma. First and foremost, if you look at this integral, we are actually integrating over the support 0 to infinity. This function here, which is it's actually a BDF, as we shall be able to establish. So it's like integrating 0 to infinity over the support 0 to infinity dx. So take outside the constants and integrate. Take out beta raised to alpha over gamma of alpha, and then you integrate 0 to infinity. So you have an improper integral. 0 to infinity x raised to alpha minus 1 exponent minus beta x is what we are doing in 5. So if you want to, if in view of now, by making the substitution, we want to get this integral. If you make this substitution, y equals to beta x. So dy is beta dx. And if you are to get your x, make x the subject, you get y over beta. So have everything now in terms of, y, So you can see I'll put here x, I'll put y over beta. Beta x here, I'll put y. Dx, you can see dy is beta dx. So dx is dy over beta. So you'll have everything in terms of y now on the right-hand side. So you shall have 1 over beta raised to alpha, and then you have this integral. And you can see this integral is gamma of alpha. This integral is gamma of alpha. As in 1, you see the mark 1. It is gamma of alpha. So you are saying the integral on the left-hand side is gamma of alpha over beta raised to alpha. So when you come across such integrals, so long as it is in standard form, like the left-hand side, don't even attempt to use integration by parts to try and integrate. we know the result. You only need to identify where alpha sits and where the beta sits. What is alpha and what is beta? And then you'll just know that the result will be gamma of this alpha, you can see the numerator, over this beta raised to that alpha. That is how we know it. Very easy to remember when this in that standard form. I repeat, to have the integral or the proper integral on the left hand side, the result is gamma of alpha. Look at the power of x here, alpha minus 1. So you identify what alpha here is. So it will be gamma of alpha divided by this beta raised to alpha. Now, in view of 5, both this integral is gamma of alpha divided by beta raised to alpha. Suppose you divide both sides by the quantity on the right hand side. In other words, divide both sides by gamma of alpha and multiply both sides by beta raised to alpha. So the right hand side becomes 1. Okay. So this beta raised to alpha will come here in the left hand side, and the gamma of alpha comes down here on the left hand side. So we are actually saying the integral of this function here is 1 over the support 0 to infinity. You can now see whatever you have here is the gamma density, what you are calling the so this is a BDF, which is actually our gamma distribution. So this is the gamma BDF type 1, the one which I stated here. This is the gamma BDF type 1, this one. This is the gamma BDF type 1. You can see how it's related to the gamma function. Now, so you can see now, in view of 5, when we are getting the MGF, you can see integral of this form. You have said just a gamma of alpha divided by beta raised to alpha. So when getting the MGF, you see, we didn't want to dissolve the form. When you come here, when getting the MGF, if you look at this integral, it is of that form. It is of that form we have just considered. Here is just 1-to-1, the same as this part. Where they differ is here. Now, instead of beta, it is beta minus t. But remember, in our usage of that integral, this one in 5, in our usage here, in 5, remember this, both alpha and beta must be positive for you to write like this. Both alpha and beta must be positive, as even indicated in the table itself. That's why I was saying the support is the first quadrant. Yeah? Alpha and beta must be positive. So you can see when getting the MGF, it requires us, so we have taken out the constants, beta raised to alpha over gamma of alpha. This is what we are integrating, which is of the form as indicated in 5. So for me to use 5, you can see where beta was sitting, I have beta minus t. But you see, in our usage, beta was positive, so this beta minus t must also, so we must place a condition for us to use that result, the Mark 5. Beta minus t must be positive, so I'm putting a condition. In other words, still we have to place a condition for this improper integral to converge. And to converge to what? So you can see, I can actually write the result of this integral using 5. You'll say gamma of alpha. Now, instead of beta, this beta minus t raised to alpha. That's why you see the result here. Beta minus t raised to alpha. But in our usage, this value here, beta minus t must be positive. Okay? Beta minus t must be positive, which in other words, we are actually saying t must be less than beta. So for this improper integral will converge to this value with this condition. Otherwise, it will not converge. So we have actually looked for it for the MGF to exist. T must be less than beta. So you can see I'm just writing the result of this integral using actually my remark 5 here. That's why I was having these remarks here. In our case, you are saying gamma of alpha divided by beta raised to alpha. Remember, this beta must be positive. So you can see instead of beta in my integral up there, it is actually beta minus t. So same story. So you say gamma of alpha, beta minus t raised to alpha, and then you simplify. Gamma of alpha cancels out. Beta raised to alpha in the numerator, beta minus t raised to alpha in the denominator. You can put them under the same power now. It will be beta over beta minus t raised to alpha with this condition. In fact, if we evaluate at t0, put t0, you can see you'll get 1. So this is so is correct. The rest you can check, differentiate, get first derivative, get second derivative, get the mean, get the second moment, get the variance. Those ones you can do. Now this is a normal distribution in general. This is the normal distribution. This is a normal distribution with parameters now mu and sigma squared, or just mu and sigma. So when I was quoting here standard normal, this is a standard normal, meaning mu is 0 here. The one we use in order to determine that gamma of a half is root of pi or root pi. This is standard, we use standard normal to establish that. Though there's another way of doing it anyway, which uses double integrals in calculus, but that one is longer. The one of using this way distribution is shorter and easier, and can be understood easily. Now, the next example is actually now the normal in this generality with the two parameters. So again, the support is the real line, is the reals, the set of reals, and the parameter space is the upper half plane. Because remember, mu also the mean, or the parameter mu lies between is also real, particularly sigma is taken to be positive. The standard deviation is positive. That's what we're talking about, that the parameter space is the upper half plane. To get the MGF, so basically from first principles, we have to integrate minus infinity to infinity, exponent tx and f of x. So this is the integration. I'm accomplishing this by I have to do some completion of squares. So I really don't want to take you through. If you talk about here, I've just substituted my fx. I get the second line. The other is just a matter of just simplifying, putting terms together. These are just simplifications. But more importantly, so you can see the first one is just after substituting fx. This is just rewriting and expanding this part, putting some common like terms together. But the second line here is where I'm completing squares. You'll see that I'm squaring and then subtract something which I don't need, which I've created in the completion. That's why it's called completion of squares. And that is where I'm able to establish that I end up with an integral which will go to 1. Because if you look at this integral, you will be seeing this of the form, this of this form, which we claim to be, it's a normal distribution, so it must be a BDF. Usually mu is the mean and sigma is standard deviation, or put in other words, sigma squared is the variance. So usually in its standard form, this is where the mean sits. In the normal, this is where the mean sits, this is where the variance sits, and this is where the standard deviation sits. So you should know normal in its standard form. That is why we were saying if you put mu 0 and you put sigma equals to 1, you get the standard normal as indicated up there. So once you're able to establish that, you can see whatever I have here is of that form actually. You can see I have this is a BDF, standard deviation is sigma, variance is sigma squared, so it's of the same form. But where I'm having mu, I have mu plus sigma squared t. So this is a normal density with mean mu plus sigma squared t and variance sigma squared. So it should integrate to one. So it's because the BDF will go to one, and then the remaining will be the MGF. The remaining will be the MGF. After simplifying, this will be the result. Try and follow step by step. But what I want you to remember when simplifying this, in the fourth step here, I'm completing squares. When you talk of completing squares, you have to remove when you create a square, you remove what you have introduced in that square. That's what you mean by completing squares. So they usually have this MGF for normal. So it is actually exponent mu t plus sigma square t squared over 2. This is the MGF for normal. You can actually see that you can always look when you look at the MGF and you see this of this form, then you can actually deduce that you are dealing with a normal random variable or a normal distribution. To check whether this is correct, you can actually evaluate it at t0 and you can see it is going to be 1. Exponent, if you put t0, you can see you get 1. So this must be correct. So you can actually, we are claiming that actually the mu here, the mu is the mean and sigma squared is the variance. So you can actually verify that using this MGF. Yeah? Get your first derivative, get your second derivative, evaluate the MGF at t0. You can see you'll get your mu. Get the second moment, evaluate the second derivative of t0, you'll get mu squared plus sigma squared. Get your var of x, you get the sigma squared. So actually the parameters you see here in the normal are actually the mean and the variance. So when variance is sigma squared, then automatically sigma is the standard deviation, which is always taken to be positive. So you can always for the basic distributions which we use all the time, know their MGFs. Also, you should be able to use those MGFs to generate the moments. So I'll pick the most common ones and actually the basic ones. Now, the next idea, so you can see also in my examples, I've used both the examples cutting across for discrete and continuous random variables. Next, we want to consider MGF of a linear function. You see, we have seen that to obtain an MGF, you require the distribution of the random variable so that you can be able to get the MGF. And once you have the MGF, you can get the moments. You can generate the moments using it. But suppose you have defined a linear function of a random variable. Must you get the distribution of the new random variable before you get the MGF? So here we shall see that you need not, if you know the distribution of the random variable, the original one, the random variable x, you don't have to get the distribution of the new random variable. If you have defined a linear function of a random variable x. So in other words, we can readily obtain the MGF of a linear function of a random variable x if we know the MGF of x. Now we know, by definition, so we are going to consider basically, we can say the two random variables. Original one is the x. I want to use mx of t so that we distinguish the two MGFs. So that mx of t would be for x. And then my of t will be of our new random variable. We are calling it y. And that y is a linear function of x. All right. The y, because you are talking MBF of a linear function of a random variable. So the random variable in question is x, and we have defined its linear function. So this way we're saying y equals to ax plus b. So why we are saying that this is linear in x, that a and b are constants. That's why we say it is linear. And of course, why is it linear? The power of x is 1. That's so we have defined a linear function of x. So of interest to us, we want the MGF of y. And remember, y is a linear function of x. So I've indicated we shall use the notation my of t, my of t, to denote the MGF of y. So by definition, is expanded of e raised to ty. By definition, and remember, t is real. In the next line, in the next line, we can in the next line, we are just replacing y by ax plus b. But remember, if you factorize exponent t into ax plus b, remember a and b are constants. So e raised to tb is a constant. Remember the linearity properties of expectation. So this will get outside expectation because expectation is an operator which is only acting on the random variable. And the random variable in question here is exponent tax. This is a random variable. This is a function of a random variable x. So this is a random variable. Constant is outside expectation. The operator e. Now, so we are saying x, the MGF of y, which is my of t, look at that, is equals to exponent tb, this is just a constant, then expectation of e raised to tax. But if you see here, the MGF of x is mx of t is exponent of etx, or exponent tx t real, as before. It's just as before. We have just used x, subscript x and y to distinguish the two MGFs here. One is for x and one is for its linear function. So it actually says here, this MGF here is mx of t. You know, if you look at the coefficient of x in the power, the coefficient of x in the power is t. But here the coefficient of x in the power is ta. So functionally, if exponent of exponent tx is mx of t, it means expected exponent of exponent tax is mx of ta. Simply put, if I know the MGF of x as a function of t, then I can replace t by ta, and I have the MGF of y. So MGF of y is my of t with exponent tb times the MGF of x evaluated at ta. This is the MGF of x, but now I evaluate at ta. So wherever there is t, replace it with ta. That's why you find here mx of ta, here will be tax, which is what I have here. So what this result is saying, if you have a random variable and you know its MGF and you define its linear function, you don't require the decision of y to get the MGF of y. We can readily obtain it if we know the MGF of x. So this is the MGF of y. I have an example here. Now, suppose I have a random variable, let us call it z, and it has a normal distribution with mean 0 and variance 1. And you have seen in this example here, we are now saying when mu is 0 and sigma squared is 1 is what we are calling standard normal. So when this mu is 0 and variance is 1, we have what we call a standard normal random variable. And you see, we can actually write the MGF of a standard normal random variable. This is the MGF of a normal random variable with mean mu and variance sigma squared. Because if you put here 0, this will vanish. If you put sigma squared here, it will be exponent t squared over 2. So this is actually the MGF of a standard normal random variable is exponent t squared over 2. Oh, so if this set as a standard number random variable, so we know it's MGF. So the MGF of z, so by definition, is expected of exponent tz is exponent t squared over 2, t real. Now, suppose I define a linear function of dz, which is standard normal, and we know it's MGF. Suppose I define a linear function of z, and I have my new random variable, let me call it x, is equal to sigma z plus mu. So the constants in question in this linear function are mu and sigma. Mu is behaving like our b here. Mu is behaving like our b here. Sigma is behaving like our a here. Our z is behaving like our x here. And our x here is behaving like our y here. So basically, I have defined a linear function of z, which is standard normal. In this linear function, I've taken my mu to be a real number, and I've taken my sigma to be a positive real number. So the MGF of x, let us call it mxt, will be exponent t mu. Remember I said b is behaving, this mu is behaving like our, these are for translation. We translate it. We actually got our y by translating it and changing the scale. B translates and A changes the scale of x when getting y. Now, we are here. Exponent T mu, MGF of Z evaluated at T sigma. MGF of Z evaluated at T sigma. Sigma is behaving like our A there. So it's actually this, we are using this result here. So exponent T mu. So evaluate the MGF of Z at T sigma. So wherever there is T, it's a place with T sigma. So it will be T sigma squared or exponent T sigma squared over 2. And if you simplify, you get that. Which is actually the MGF of normal with mean mu, the one we have just found here. This one. You can see that's actually the MGF of normal with mean mu and variance sigma squared. This was an early example which says that if you have got a normal random variable, a linear function of a normal random variable also has a normal distribution. A linear function of a normal random variable also has a normal distribution. So we write x as a normal distribution with mean mu and variance sigma squared. The way we could have also said the same here when we write for normal here, we say x with that tilde symbol and then you write capital N bracket mu comma sigma squared bracket. The way we write for the others, like Poisson, we just say Poisson bracket lambda, binomial NP, and so forth. No certain ways of writing these distributions, and you can always Google them. So this example tells us if you know the MGF of a random variable, and then you define a linear function of the random variable, you can readily obtain the MGF of the linear function of that random variable. You don't have to determine the distribution of the new random variable. So it makes work very easy. Now, how is X not just just to tell you something else? How is X related to Z? You can actually see that if X equals to sigma Z plus mu, you can see if you subtract mu from both sides and you divide it by sigma, you will get X minus mu of a sigma is Z. Meaning if you have a random variable with mean mu and standard deviation sigma, if you subtract its mean and you divide by standard deviation, we say that random variable is standardized. It is actually standardized. So Z is a standardized random variable in this case. And in particular, because it is normal, that's why we call it standard normal. And a standardized random variable will have mean 0 and variance 1. You remember when you were talking about those moments, we talk about standardized moments. Standardized moments. Here, you have an exercise which you need to do. Geometric distribution, where we had seen this before. I want you to determine the MGF of X and use it to find the mean and variance. Determine the MGF of that. Determine the MGF of Y. You can see Y is X minus Y and use it to find its mean and variance. You can see Y is a linear function of X here. And they are related to what we were saying, to the Bernoulli experiment. You know, remember when you talk about the number of trials before the first success, and the number of failures before the first success, you relate to those things. You can see they were tested. You will be able to see something here. In fact, the two distributions will have the same variance, but they'll have different means. Because you can actually see here, we are not changing the scale, we are only translating. So they'll have different means, but the same variances, the same variance, I mean. So fine, do that, do these exercises. 2A, another variable X has uniform chain over the interval. Determine the MGF of X. Remember, this is a special case of the uniform. We had a uniform AB. A is minus 1 now, and B is 1. And use it to determine the spread of X and var of X. So you have to be cautious here. You have to be cautious here when you determine the MGF. It will have a singularity. So you know what we are supposed to do, as explained in that example we considered for the uniform. Under B, determine the MGF while my of t of the random variable. So I have defined a linear function of X. So in A, we know the MGF of X. You say you have found it. And then I've defined a linear function of X as indicated here. Remember, A and B are constants, but in this case, A less than B. So if A and B are constant, these also are constant. These also are constant. So this is basically a linear function. This is for translation, and this is for changing the scale. So I'm saying determine the MGF of Y of this random variable and deduce its probability distribution. After you have found this MGF, you should be able to recognize its distribution. We already have that MGF somewhere here, you know, because an MGF uniquely determines a probability distribution. So I want you to determine and see whether you can recognize it. Very important. I want to see whether you can recognize and relate and say this belongs to this distribution. So that it also brings out actually another important aspect of MGFs. It can help you identify the distribution. So do this. And it's important, I was indicating that don't leave these exercises to accumulate. They can be overwhelming when you don't do them immediately. And then towards the end, you find you have not done them and things are not clear in your mind and we cannot come back to them. There'll be other things to be done at that point in time. So let us move together. When you say do the exercise, do. Mm. We now move to a very important area also. We have discussed distributions and basically the univariate cases now, but we want to extend that same that concept to bivariate distributions, meaning we are going to be studying two random variables simultaneously. And this is just the case of introducing what generally we call inside multivariate distributions. So when you talk about bivariate, you are talking about two, can be extended to trivariate, and even in general, k-variate, where k is arbitrary. And more importantly, it will be the idea of bringing in the idea of marginal distributions and also conditional. So for one to be able to study conditional distributions, we require at least two random variables. So we have to discuss uh, two random variables simultaneously. Unlike, say, for the univariate case, you only deal with one. So bivariate distribution. So formally, we have been considering random variables which take values on the real line. That's why we're saying take values in R in general. Of course, we saw with particular examples they can take in some interval of R or some subset of R and so forth. So, but in general, they are actually taking values on the real line. We shall now study and consider the properties of two random variables simultaneously at the same time. So the chain probability distribution of two random variables is called a bivariate distribution. So the ones we have been considering are called univariate one. So the joint distribution of two random variables is called a bivariate distribution. So the study of bivariate distributions increases the scope of applications or probability distributions. You know, it will increase the scope of its applications. You remember when you were studying univariate, a number of aspects of calculus were assumed, known. Similarly here, so that's why we were dealing with, say, differentiation, integration, series, and so forth, convergence, and blah, blah, and all, etc. They were assumed known. Eh? In the same line of thought, we also have assumptions here regarding calculus techniques such as partial differentiation. They are assumed known. Double integration are also assumed known, that kind of thing. Uh, when you are dealing with the discrete and variables, you ended up with series, you know. You also had integrals. You ended up also with improper integrals. Those are calculus aspects, but we need them in probability because they are tools. You must also be able to manipulate double summations involving finite and infinite series. So you can see when it comes to calculus, usually calculus deals with the continuous. And then also when it comes to, you can see when it comes to the discrete random variables, you can end up with finite or infinite series. And originally we were talking about series with one summation. You can also have series with double summation. The way you have an integral, you also have double integrals when you are dealing with continuous. Mm. So that's definition. So when it comes to uh, studying more than one random variable, the simplest case is bivariate random variable, which is actually two-dimensional. So unlike univariate cases, which are basically scalars. So when you are dealing with a random variable, just one, you are actually dealing with a scalar. But when you are dealing with more than one, you are dealing with a vector. And because it is random, we refer to it as a random vector. So when this two-dimensional, we call it two-dimensional random vector. And then we can be extended to three-dimensional, four-dimensional. And then we can even say in k-dimensional random vector, that means it's of dimension k, where k is arbitrary. So that when you know the general aspects of a k-dimensional random vector, all these others are will end up being special cases. If you say k equals to 1, you'll have the univariate. If you say k equals 2, you have bivariate. If you say k equals 3, you have trivariate, and so forth. So let us define a two-dimensional random vector. Let x and y be two random variables. These are the random variables of interest to us now, 2. And remember, when you are talking about random variables, they emanate from some random experiment. So random experiment are associated with a sample space. How we are defining the random variable. So let x and y be two random variables defined on the same sample space. Then the ordered pair xy, x is random, y is random, is called a two-dimensional random variable. Two-dimensional random variable or a two-component random vector. All right. So you can see it is written as capital. You can see they are uppercase. Both they are random variables. And you are saying this ordered pair. You cannot keep on swapping because you are saying the random variable x will take the small value x and the random variable y will take the small value y. So this ordered, an ordered pair, so that there is no confusion what x is and what y is, the lowercase. So the value of the random vector are denoted by xy, now lowercase x and y. So lowercase x is the value assumed by the random variable x, and lowercase y is the value assumed by the random variable y. The random vector, with that, remember now, have that in mind, there must be uppercase, takes values in the two-dimensional real space. Two-dimensional real space, what you usually call R2. R2 is R cross R. You see, like when you are dealing with a unified case, to taking values in R. So two-dimensional random vector is taking values in R2. Usually a two-dimensional real space. We usually just call it R cross R, or simply put R2. R2 is R cross R. It's a plane. So basically, we are actually saying we have this ordered pair in two dimension. In two dimension, we are saying we call it, it's actually a point in R2. You know, when you are in R, you say you have a point. It's just a real number is a point in R. But now, when you are talking about R2, you have this like coordinates is a point in R2. Can be extended, usually of n dimensional. So you are talking about a point in Rn. So that point has got it has got is of dimension n. It's a vector having the components n of them. Let me use an example to just bring some point home. Of course, when you are talking about random experiment, so when you are talking about random experiment, it has to associate with the sample space. There is a possible scenario here. Suppose that a fair die is tossed once, and a number on the face that shows up is noted. So you know what a die is. Those in the face is 1, 2, up to 6. So we have a random experiment associated with it. We shall have a sample space. And then we have defined, and then we need to define two random variables. That's what we mean by saying we are studying two random variables simultaneously. Of interest to us later will be what will be its probability distribution. Suppose that the fair die is tossed once. Remember, the die is fair, balanced, or unbiased. And the number on the face that shows up is noted. Now we want to define our random variables. Let x be the number on the face that shows up. So we have defined our random variable. We even know its possible values. And let y denote twice the number on the face that shows up. We have defined another random variable. Then xy, that pair, is a two-dimensional random variable with possible values. You can see the way we are now writing the possible values xy. That's why we are calling an ordered pair. The lowercase x will be the value assumed by the random variable x, and the lowercase y will be the value assumed by the random variable y. And remember what x is, the number on the face that shows up. So when you toss a die, what are the possible values of x? The face that shows up. We shall be having 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 will be the possible values of the random variable x. And let y denote twice the number. So you can see it says y is twice the number on the face that shows up. So that if x takes 1, y will take 2. If x takes 2, y will take 4, like so and so forth. So twice the number. So these are the possible values of the random vector xy. These are the possible values of the random vector xy. 1, 2, 2, 4, 3, 6, 2, 6, like that. Each with probability 1/6 because the die is fair. Each with probability 1/6 because the die is fair. Now, let us consider another example. Now, let me bring in the aspect of a continuous one so that we bring it the whole idea home. Consider the experiment of choosing a point at random from the rectangle. So we have a rectangle here, call it R. So the rectangle will comprise the numbers xy, say that x lies between AB, the interval AB, and y lies in the interval CD. Let x denote the first coordinate of that point. We have a point here. We have the coordinates. These are the coordinates. The one is for x, the first is for x, and the second is for y. Let x denote the first coordinate and y denote the second coordinate of the point so chosen. Then the pair xy represents a two-dimensional random variable with possible values in the rectangle. You see now, this random vector will take possible values in R, which is a subset of R2. You can see where the possible values of the random vector is now. These possible values are actually in R. And you can see it's a subset, it's a rectangle, a subset of R2, a subset of a two-dimensional real space. As I have just indicated, of interest to us is actually what is the probability distribution of the random factor. So this brings us to talk about what you call joint distributions. And we start with discrete joint distributions. Consider two random variables x and y defined on the same sample space. So they must have emanated from the same random experiment, is what I'm saying. A two-dimensional random variable, xy, is said to be discrete if each of its components, x and y, is a discrete random variable. So we call this two-dimensional random variable discrete if both of them are discrete. For instance, in our example 1, we have a discrete random factor here. Both x and y are discrete. Example 1 describes a discrete random factor. If both x and y have discrete distributions, then xy is said to have a discrete bivariate distribution. So x has its own discrete distribution, y has its own discrete. So the pair now is said to have a discrete bivariate distribution. Equivalently, we may say that x and y have a discrete joint distribution. So when you say bivariate distribution or you say joint distribution, they mean the same thing basically. It's only that the first one actually indicates there are two. When you say joint, say you are it is known. If you already know the dimension, then you just say joint distribution. But joint distribution is more general because you can have joint for 3, you can have joint for 4, and so forth. So the chain probability function of x and y is defined, so they are making it more general, is defined to be the function. Remember before when you are dealing with univariate, you are just saying a function of x. Now we are dealing with 2, we say a function of x and y. Say that for any point xy, now when you have as a pair, we are calling it as a point in R2. It's a point in R2. This is how it is defined. F of xy is defined as, so the function, remember before you were saying f of x was probability that the random variable x is equals to small x. That was how you are defining the function, which you are calling actually probability distribution. So when we extend it to 2, or the bivariate case, we have our function, which is a function of two variables, is a function of x and y. So this is the function, and that is how it is defined. Okay, see, we are talking about actually a joint probability. Probability that x takes small x, comma, y takes small y. That's why we are talking about joint distribution. You can actually see we are having what you call a joint probability. So if the point xy is not one of the possible values of the pair of random variables xy, then f of xy is 0. That's why you are writing also when you are dealing with uniformity, you are saying 0 otherwise. You have the function defined over its support and 0 otherwise in a similar manner. Also, if the sequence, say x1, y1, x2, y2, and so forth, introduce all the possible values of the pair, then if you sum over the possible values, you will get 1. If you sum f of xi, yi, for I equals 1 to infinity, you will get 1. Let us look at it now in more generally. The joint probability function of the random factor satisfies. For it to be called a probability function, and you know what you are calling probability function is basically actually a distribution, you know, you call it joint distribution. It's actually a probability function. It's actually a distribution. So we are actually extending how we define for the univariate case. One, you can actually say the one also says this function is non-negative for all points in R2. That's why we were saying here, it will be defined over the support and 0 otherwise. Outside the support, it will take the value 0. So there is no way it can be negative. So for all points in R2, it is non-negative. And if you sum over the possible values of the random variables, that means over the pair, you will get one. That is why now this will be called a joint probability function. You could call a probability distribution. So you find here now we have a double summation over x and over y. So the double summation ranges over all points xy in the two-dimensional real space, over which the function f is defined. So you'll actually be summing it over the support. Outside the support, it will take the value 0. Now, suppose you take a particular subset of R of the real space, two-dimensional of R2. You want to find the probability that the random vector takes values in that subset of R2. So suppose you call it, you have a subset E of the two-dimensional real space. The probability of the event that the random vector takes values in E, that subset of R, is given by. So we are saying the random vector, probability that the random vector, which is xy, takes values in E. Then you are going to sum the function, the probability function. Remember the double summation of x and y for all points in E. That means you have actually gotten a probability that the random vector takes values in E. So you have actually found the probability of this event. The event in terms of the random variables. You have the event in terms of the random vector. The event in terms of the random vector. So you have actually, so you are saying sum over possible values of x and y, so long as the point in R2 is in E. This point in R2 is actually inside E. So you are summing over all points in E. Let me bring in another example so that we can capture something. You see, we are moving towards talking about distributions, and we are now discussing the discrete random vector. Example number 1. Each of two balls contains 5 identical discs marked with the numbers 1 to 5. Each of two balls contains 5 identical discs marked with the numbers 1 to 5. So there's one ball contains identical discs marked 1 to 5. Another ball also contains identical discs marked 1 to 5. Two discs are drawn at random, one from each ball simultaneously. So you put your left hand to one pole and the other right hand on the second pole. And then you are going to draw two discs, one from each pole. Two discs are drawn at random, one from each pole simultaneously at the same time. Let us define our random variables. Let x denote the maximum of the numbers on the discs drawn. Let x denote the maximum of the numbers on the discs drawn, and y the sum of the numbers on the discs drawn. We have defined two random variables. They are already defined on the same sample space. They emanate from the same random experiment. So when you hear me talk about the same sample space, then they must emanate from the same random experiment. The act of drawing the disc from the two balls is a random experiment. You actually don't know which disc you will pick. Yeah. That's why it's a random experiment. We use these examples to capture the concept of randomness, to capture that uncertainty. The sample space of the random experiment contains 25 equally likely points, each occurring with probability 1 over 25. You see, you can see the whole idea of classical definition of probability comes in here, because actually the discs are identical. So there's no bias in picking any one of them. They are the same, they are of the same size, they are identical. That's why the concept of equally likely comes in. So the sample space of the random experiment contains 25 equally likely points, each occurring with probability 1 in 5. And here is that sample space. This is a sample space of the random experiment. You have pole 1 is 1, 2, 3, up to 5. But there are 5 disks in the ball. We have pole 2, there are also 5 disks in the ball, 1 up to 5. Whatever we have now inside there, those are the sample space of the random experiment. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. You can see you can pick number 1 in ball. When you pick in ball 1, you can pick 1, and in ball 2, you can pick 1. You can pick 1 in ball 1, but you pick 2 in ball 2. So this the first row is when you pick 1 in ball 1, but you pick 1 in ball 2, and then you pick 2, then you pick 3, you pick 4, you pick 5. You can pick 2 in ball 1 and 1 in ball 2, like that, like that. So actually 1, 2, and 2, 1 are different. That's what you were saying, the ordered pair. They are different points. There are also scenarios where you can pick 2 in ball 1, you pick 2 in ball 2. You can pick 3 in ball 1, you pick, so you are picking the same numbers in the different balls. This is a sample space. 25 sample points. Each with probably 1 over 25 because they are equally likely. These disks are identical. Now, we are now defining the random factor. Let X denote the maximum of the numbers on the disks drawn and Y the sum of the numbers. So when we get possible values of the two random variables, which we shall be able to enlist the possible values of the random factor. So the possible value of the random factor will be given by the pair as indicated here. So you'll go, it says, for instance, if you are here, you see, it says the X will be the maximum and Y is the sum. So when you have 1 and 1, the maximum is just 1 and the sum is 2. So you can see X will be 1, but Y will be 2. If you come here, between 1 and 2, the maximum is 2. So X will be 2 and the sum is 3. So X will be 2 and Y will be 3. That's why you see these 2, 3. You do the same for all the points. You can see when you are here, 5, 5. X is 5, but Y is 10. The sum is 10. So you can see you have these are not the possible values of the random vector. Each with probability 1 over 25 because the sum of points there were equally likely. So each with probability 1 over 25. So we have actually defined xy is a discrete random vector. Now we talk about the joining probability distribution of x and y is, now remember what we are calling that joining probability function. So each one of these points here occurs with probability 1 over 25. So you can see for the points like 1, 2, 2, 4, 3, 6, 4, 8, up to 5, along the diagonal, for those points along the leading diagonal, 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. Each one has got probability 1 over 25. You can see that's why I have it here. So I'm giving xy, because those are the points along the leading diagonal. For the others, you can see you have 2, 3 here, 2, 3 here. 3, 4, 3, 4. It's like actually, you can actually reflect along the leading diagonal. So this is 1 over 25, 1 over 25. So 2, 3 will be having 2 over 25. And similarly for the others, each will, except the ones along the leading diagonal, the others will be having 2 over 25 because you can see, eh, you can reflect along the leading diagonal. So you are saying for others, it will be 2 over 25. These are the cases. 2, 3, all these would be having 2 over 25. And if you are to sum all these probabilities, you should be able to get 1. We have actually defined what we call a joint probability distribution of X and Y. That is why we're saying here now is where outside the support, you are saying 0 otherwise. That is why we are able now to say for any point different from this, in the bivariate sense, any point different from this will take the value 0. That's why we are saying 0 otherwise. Mm. If you take any other value in R, the value, a point in, of course, in two-dimensional case, in the two-dimensional sense, they are not, is not among these, it will be 0 otherwise. If you are to define an event, for instance, suppose I define the way you are doing for the seeing univariate case, how we define events in terms of a random variable, you can actually see, suppose I define an event E would comprise these sample points 2, 3, 3, 5, 4, 8, 5, 8, 5, 10. So you can see the probability that the random factor xy takes values in E, takes these values now, you sum the probabilities of these points. You just have to check 2, 3, 2 over 5. You can see there. 3, 5, where is 3, 5? 3, 5 again is 2 over 5. 4, 8 is 1 over 5. Then you exhaust. Then you get 8 over 25. So if you have actually found the probability that random factor takes values in E, in other words, like actually we have found the probability of the event E. Now, equivalently for the discrete case, we can always also represent our probabilities or the joint probability distribution using a table. And this is exactly what I have here. You can actually see I have an array. Of course, it can be very cumbersome if you have got so many possible values of the random variables. You can really have a very big array, but usually there is no need to do that anyway. It suffices to write in a more compact form, the way we have written here. This is more compact. But just to illustrate that joint probabilities, especially in the bivariate case, can be actually represented using a table. And the same idea you can visualize even when you are dealing with three random variables, the trivariate case. It's only that it will be in 3 dimensions. It's very easy to see 2 dimension. And you can visualize even 4 dimension, though you cannot see with your eyes, you can conceptualize what I'm talking about here. So it's very easy to see because 2-dimensional is very easy to see. You can actually see with your eyes. Even 3 dimensions, we can actually draw it. But generally, we can always even talk about multivariate case, though we may not see them with our eyes, they exist. So you can now see that I have the random variable x, and you see whatever I have here, these are the possible values of the random variable. And I have here the random variable y. If you look very closely, these are actually the possible values of the random variable y. Actually, they came from, if you look at the possible values of x, from here, look at the possible values of x. The first coordinate. The first coordinate are the possible values of x, and the second coordinate are the possible values of the of y. So you can actually capture, you can see for x just 1, 2, 3, 4, 5. Mm. And then you can see for y starting from 2 to 10. Mm. You can see from for y it is 2, 3, 4 up to 10. And I've actually put what I have inside the table. Those are now what you call the joint probabilities. Mm. You can see for 1, 2, for 1, 2 is 1 over 25. That is why you see 1 over 25 here. But for 2, 3 is 2 over 25. 2, 3 is 2 over 25. That's why you see 2 over 25 here. You do the rest for all of them till you reach like 5, 10. Where is 5, 10? 5, 10 is where? It's 1 over 25. Like that, like that. All that. Where we have zeros, the random factor don't take those values. The random factor does not take 1, 3. That's why you find it is 0 here. The random factor does not take 2, 2. So the 0 otherwise, where you see zeros is what you are saying, 0 otherwise. And of course, and then the other values which are different from what we have here. So you just put zeros. Mm. What is very interesting now, like if you sum all these probabilities, the trade probabilities, you'll get one. Mm. And I'll use this also to illustrate that if you sum along the rows, if you sum along the rows, you have these probabilities. And if you sum along the columns, you have these probabilities. Again, they will sum to 1. And again, they will sum to 1. You will find that whilst these are the what we have inside are the trade probabilities, meaning for the random factor, xy. You will find that these are the probabilities for the individual random variable x, and these are the probabilities for the individual random variable y. So this table, what we have inside are actually the chain probabilities, the ones we have here. I've added the last column and the last row. The last row is basically the sum along the columns. And the last column is basically the sum along the rows. Whatever the case may be, the train probability sum to 1. For the individuals, random variables also they sum to 1. So we are actually saying from the train probability level of xy, we can also obtain from the individual probability of x. That is probably that x equals x are given. So when you have a chain, you can also go back and even get for the individual. You don't say it, probably that x takes 1 because 1, 2, 3, 4, 5 are the possible values of the random variable. So probably that it takes 1 will be 1 over 25. Probably that it takes 5 is 9 over 25. Probably that it takes 3 is 5 over 25. If you go for the y, the both values of y are 2, 3, 4 up to 10. The probability that it takes 6 is 5 over 25. The probability that takes 9 is 2 over 25. The probability that takes 4 is 3 over 25. So basically, we have a probability distribution here as far as y is concerned. We also have a probability distribution here as far as x is concerned. So meaning, when we have a joint probability distribution, we can always get the distributions of the individual random variables. Namely, probability that x equals to x and probability that y equals to y. This is for x and this is for y, the way I've indicated here. So these are the chain now which you could write it. Probability x equals to x comma x equals to y are the ones inside. So more precisely, this is how we get now probability that x equals to x. What do? You can see now we have been, for us to get these probabilities, we were summing over y. You can see we were summing like this, so we were summing over y to get this. So it's like, for us to get these probabilities, sum the joint over y. And to get the margin, the probabilities for the y, sum the joint over x, because we were summing like this to get for the we are summing over x so that we get for the y. Now, from the chain, we can see from the chain probability distribution, we get the individual probabilities. These are actually probability distributions. As we have seen here also, this example, they sum to 1, meaning they are also probability distributions for the univariate cases. So the right terminology for these distributions, we call them the marginal probability distributions of x and y. So we call them now the marginal probability distributions of x and y, respectively. This for x, this for y. Now, the joint. So this is the notation which we are using for the joint probability distributions f of x, y. The ones now I was telling you what you have inside the table are these joint probabilities. This is how we are defining our probability function a few minutes ago. F of x, y is probability that x equals small x, comma, y equals small y. These are joint probabilities, giving us a joint probability distribution because they sum to 1. And they are non-negative, they are probabilities, of course. So we shall adapt the following notation for the marginal probability distributions. So this is a notation we are using for the joint, and for the marginal probability distributions, we shall use the notation. So that we are able to distinguish the two marginal distributions, we shall be using here f subscript x of x to denote the marginal for x. And we shall use f subscript y of y to denote the marginal of y. And you have seen that once we have the chain, we can get these two. The way we are having here, if you sum along the rows, you can sum along the columns, you get those distributions. So from the chain, we can actually get the marginals. To get for one, you sum over the other. That was example number 1. I want to use another, fortunately I have another example here. Example number 2. And you can see this one now, I've given it just in functional form. Okay. If you saw example 1, we actually described the random experiment. We called the sample space. We defined the random variables, and then we saw the possible values, and then we ended up with a distribution. In example 2, the way we are doing for univariate also, we say you can actually start from a random variable without really, we were not really bothered with the random experiment. So long as that function satisfies the two properties that must be non-negative and sum is to 1, then basically you will have defined a joint probability distribution. So when I say in example 2, x and y are discrete random variables with joint probability distribution. F of x, y is given by that function. We are saying x is 0, 1, 2, 3, and y is 0, 1, 2, 0 otherwise. Meaning if you sum over x and y, you should be able to get 1, which I'm demonstrating here. And remember clearly what we have written here, or what we have here, is non-negative. It cannot be negative. So you can actually see here, if we sum, you can see these are double summation. You can see the support, x is 0, 1, 2, 3, and y is 0, 1, 2. Fortunately, this example, the numbers are consecutive. So you are actually saying you are summing y from 0 to 2, and you are summing x from 0 to 3, like that. Go and simplify, you see you'll get 1. It doesn't matter. This one we are summing over x and then y. You could as well sum over y and then x, doesn't matter. You will still get 1. Doesn't matter. You can actually see, suppose we want this probability. You can see this probability talks about x less or equals to, which if you have the marginal of x, then you can just use it. If you have the marginal of x, you can actually get the marginal of x and then you use it, because it will mean x less or equals 2, and you can see both x takes 0, 1, 2, 3, it means actually x takes, you are saying x takes 0, 1, and 2. That is why you are going to be adding for x0, for x1, for x2. But you see, when you are saying x is 0, you can see y takes all the possible values. So you must sum over all the possible values of y. X takes 0, but you sum over all the possible values of y. X takes 1, sum over possible values of y. X takes 2, sum over possible values of y. So if you simplify this, you simplify that, come down, you'll come and get the result, 0.6, 18 over that. And you can actually see in tabular form, if I could represent like in example 1, I can have these probabilities in a table. Those probabilities are the probabilities inside the table. These are the possible values of x, 0, 1, 2, 3. These are possible values of y, 0, 1, 2. And the way you represent your array, doesn't matter where you put your x or where you put your y. If you look at this one, this example here, put here my x here, put my y. It was just to have a proper orientation, because I didn't want this table to cover all page. If I put y here, there are more terms there. It will be reaching around here. So I put x here, so that is horizontal. So long as you know where your x and y is, you can now see this one is the other way around. Put here my x and y, because it's long along. That's how I put x, I put y. So long as you know where they are, you know there's a change here. This will be for the marginal of x will be here, marginal of y will be here. And this other one, you could see it was the other way around, depending on where you are. This marginal of x is here. So it's not fixed. That one is why you want to arrange them. It depends on one. And me, I was using, I would look for the best way so that I don't have a whole table like this taking a whole page here. Now, you can see we have found a probability that x is less or equal to, and you can see this one, if you had the marginal of x, we could just get it readily as in the univariate case. It's just some probabilities for the individual values, and we are done. We have found 0.6. You can actually see here, if you look at this, possible values of x 0, 1, 2, 3, possible values of y 0, 1, 2, sum along here, along the rows. If you sum over x, you will get the marginal of y. If you sum over y, you'll get the marginal of x. So if you look at possible values of x is 0, 1, 2, 3, possible values of y, you can actually see that we have found it to be what? X less or equals to 2, 0, 1, 2, 0, 1, 2, you have got to be 18 over 30. And if you use the marginal of x, you'll get it. You'll get actually x taking 0 is 3 over 30. X taking 1 is 6 over 30. X taking 2 is 9 over 30. 3 over 30 plus 6 over 30 plus 9 over 30. That is 18 over 30. This is what you had here. So you can see if you had, but you see, we had to get through the bivariate case, because when you are saying x equals 0, x takes 0, but over all the possible values of y. That's why we end right here. And then you can actually see what you are getting is actually correct. Here is an exercise for you. For the following join probability distribution of x and y, so these are the joint probabilities inside. These are the marginals. I've given them in the form of a table. What you need to notice is that if you sum all the probabilities inside the table, you will get one. If you sum with the marginal, you'll get one. If you sum with the marginal for the other one, you'll also get one. So we have got three probabilities. We have the joint and the marginals. Find these probabilities. Some look like joint, some look like marginal, but you need to get the right probability. Because we have marginals here, when getting the marginal, you can get them directly. But you need to be more careful when you are getting for the joint. Find those probabilities. These are examples where the possible values of the random variable are consecutive. That's why you are saying you are summing over. Very easy, you say sum from 0 to 2 because they are consecutive. But that don't mean that when you are talking with random experiments and possible values, they are always consecutive. They may not be consecutive numbers. And this is the example. For the following chain proposition of x and y, you are told x takes minus 4, 2, and 5. Y takes minus 3, 0, 4, and 12. Those numbers are not consecutive, but those are the probabilities. They take those numbers. X taking minus 4 and minus 3, that's a probability. X is taking 5 and Y taking 12, that's a probability. Like that. So this probability, if you sum them, they will go to 1. You can also get the marginals and if you want, or if necessary. Find the probability that Y is odd. I believe what you know what you mean by a number is odd. Find the probability that XY is odd. And if you look at it, you can see X can also take a negative number. Also, Y can take a negative number. Find the probability that X is positive, but Y is non-negative. This is joint probability. This is joint. This is marginal. Do those ones. So the foregoing was to do with a discrete random factor in the bivariate case. That's what we're talking about, discrete joint distributions. Now we want to talk about continuous joint distributions. Consider two random variables x and y defined on the same sample space. Then the two-dimensional random factor xy is said to be continuous if each of its two components, x and y, is a continuous random variable. Thus, if xy is a continuous random factor, then it assumes values in a subset of R2. We are talking about that. For example, consider a rectangle R. So this is a subset of R2. This is a subset of R2. X takes values in the interval AB, and Y takes values in the interval CD. So we have a rectangle. And suppose XY assumes values in R, subset of R2. Subsumes values here. This is the support basically. Then XY is a continuous random factor. If both X and Y have continuous probability density, now when you're talking about continuous, we now bring in that concept of density functions. We don't talk of density when you're dealing with discrete. So if both X and Y have continuous probability density function, you are calling it BDFs. The next one is said to have a two-dimensional or bivariate probability density function. Bivariate BDF, or you can say two-dimensional. Let us now suppose that the continuous random factor xy assumes values in a region R, subset of R2. This is the region. Say that the probability the random factor xy takes values in R is 1. So it's actually taking values in this R and not outside. That's why we're saying the probability that random factor takes values in that R is 1, meaning it takes values in R and not outside. But we are now defining a sure event here. Suppose that this unit probability is when you are dealing with discrete, you are summing over possible values. But when you are dealing with continuous random variables, it does not really take particular values. It's continuous. So we cannot really apportion that one discretely. That one, that unit probability is continuously distributed over the region R. Is continuously distributed over the region R. The total probability of 1 is continuously distributed over the region R. Our aim is to obtain an expression the way you are doing for the discrete. You can see for the discrete, we are just looking for the possible values. We get a sum of points which are in E, and we sum probabilities for those points. But how do we deal with the situation, this kind of situation, when we are dealing with a continuous random factor? So our aim is to obtain an expression for, in a similar manner, that the probability of that random factor takes values in E, and and this E, the event or the subset E is a subset of R. But the total probability of 1 is distributed continuously over that region R, the rectangle. Suppose now we have a subset of that region. It takes values in the region with probability 1, because that is where it takes values. It does not take values outside. How about when you want to deal with a subset of that R? So the probability would be less than 1, of course. What would be, how do we get that probability? So E is a sort of R, the rectangle. So the region R may be depicted as shown in the figure below. The region R may be depicted as shown in the figure below. This is what I'm talking about, the region. We are in R2. There is a region R, okay, in R2. This is R2, R cross R. So we have a region. So I'm depicting that region as R. And I made this just not to take a particular shape as such, just a region. The simplest you can talk about could be a rectangle. But I'm talking of a region in general. Just a region is a sort of R2. So I pick whatever shape. So for the sake of argument, I pick just say this is the region of interest. This is R, which is a subset of R2. Now, in that region R, we want to consider an element of area. This del R is an element of area. It is the area having the sides of that area, the length of the sides. On the x-axis is a small del x, and on the y-axis is a small del y. So actually, if I have to get the area, this small element here, small, it actually small, del x is small, del y is small, I also have a small area, some element of area in this area. So my element of area, which I'm calling del r, will be del x times del y. You get that element of area. Now, let del p be the element of probability over the element AR. So we are actually saying the random factor will take values in that element, that area of del R, with this probability, small probability del P. So let del B be the element of probability over the element del R. So the random factor will take values in that element with that probability. Small area with small probability. Then we have these now. These are now the calculus. That this limit exists. If we make, we are actually saying, if we make your area very small, we also make the element of probability to be small. So we say in mathematics, in the limit, as del R and del P tend to 0 of del P of del R, the limit will be called in calculus dBdr. Will be called in calculus dBdr. It's like differentiating P with respect to R. The derivative of P with respect to R is what we call f of xy. That is why you are now calling it a density. That is why we are calling it probability density at the point xy in R. See? You can see the concept of density you are using for the invariant case. Now we are using now here for the continuous also. That's why we are calling it probability density at xy. This is a point. So I don't know when you talk about point in two dimensional, you say it's a point in R in the two-dimensional sense. Therefore, if dBdr is f of xy, it means dB is f of xy times dr. Get that, mathematics. dBdr is f of xy. So dB means f of xy dr here. But in the limit, remember, del r is del x times dy. You know? So as also as del r tend to 0, del x tend to 0, del y is also then, when it is becoming small, del x is also becoming small, del y is also becoming small. So we are actually saying in the limit, because del r is del x del y, what it actually means is that dr will be dx dy. Calculus comes in now. So dB is above xy dr from here. Now dr will be dx dy, because remember del r is del x dy. So dr will be dx dy. So my dP here will be f of xy dx dy. So if I want to find the probability that the random factor xy takes values in E, that is, we want to find the probability of that event, whenever E is a subset of the region R, we have to integrate over that set E. So what you are calling dP, it is like probability, it is like, this integral is like summing probabilities continuously. No, integral is like, in the continuous sense, actually, up in the why this the notation, that symbol is the way you know the history about integral. It is actually came from the word summation, and then it was elongated to look like to mean that you are summing things continuously. So it was like it's like you are summing like small elements of probability, which you could be calling del p, but now continuously it will be an integral. So you are saying integral dp. If you integrate dp, you get p probability. But you are now saying dp over the set e. But dp is f of xy dx dy. So I'm saying I'll have to, now I end up with a double integral, because it's over the points xy, because you do dimensional. So it will be double integral over that e of f of xy dx dy. This is how I'll get that probability. So it means to get the probability that random factor x values in E, I require their joint probability density integrate over E with respect to x and y. And we have our probability. So a two-dimensional or bivariate probability density function for the random factor xy, assuming values in a region R, which is a sort of R2, is a real valued function f of xy and satisfies. That's the way we did for the discrete, non-negative for all xy in R2. Because it takes values in this region R, it means probably that x, the random factor that takes values in R, we had said it is 1, because it takes values there. We had said it takes values there and not outside. Meaning, if you integrate over R, that region, the joint PDF with respect to x and y over the region, you get 1. You have actually defined what you call now the joint probability density function of x and y, or basically the probability density function of the random factor xy. They mean the same. Those phrases mean the same. So f of xy is called the joint probability density function. You could just call it the BDF of x and y. The joint BDF of x and y, and it suffices. When I was depicting this figure here, I didn't have to imagine that is regular or whatever, just some shape, some region. But suppose it is a very regular figure, suppose in particular, suppose it was just R, suppose it was a rectangle. In particular, it is very nice. In particular, if R is a rectangle, as envisaged earlier here, suppose it was a rectangle. This is more general here. When you are considering it is a more general figure, suppose in particular you are dealing with a rectangle, what you are actually saying, you integrate over R. And because it's a rectangle, you know the limits very well. The limits for x, AB, the limits for y, CD, you will just integrate the joint over x with respect to the limits of x, AB, the joint with respect to y for those limits CD, it will be 1. You see? Yeah. You have this definite integral. We are saying to go to 1. Now, let me see how far this can be, whether it's what going on or I summarize. Oh, let me finish or I leave you that exercise. And then, oh, great. Then we start marginal to next time. Then we start marginal next time. And these are very simple examples, so it doesn't worry me. Look at this example. Look, example. X and Y have the joint BDF. F of xy is 1. This okay. In fact, it's not. We are saying this is a rectangle basically. This is a rectangle, but more so is a square. Because it's equal 0, 1, 0, 1. It's a unit square in the first quadrant. The support is the unit square in the first quadrant. And because it's continuous, it doesn't matter. You can see the way you are writing here. A less than x less or equals to b. You remember before you are doing for univariate, whether you say when x is continuous, doesn't matter whether they are saying a less than x less or equals to b, or you say strictly less than b. It doesn't matter. So this is a unit square in the first quadrant. Exactly a square, very regular figure. So if you integrate over that region, you expect to get 1. You can see here I'm saying dx dy 0 to 1 dx. So with respect to x, whether you say with respect to x or respect to y first, doesn't matter. You see. So you can see if you integrate over that f of xy over the support, you get 1. So exactly, it's a BDF. If I want to get probability, so if I want to get probability that x is less than a half and y is less than a half. So what it actually means, because x lies between 0 and 1, here means here x lies between 0 and a half, and y lies between 0 and a half, which is that blah 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 blah. You get a quarter. Now, here is if you look at this x plus y, this is x plus y is less than 1. You need to identify the region now. It's just straightforward, because here you can see uh, the limits were not dependent on each other. But the moment you write like this, you find that the limits will depend, or one variable will depend on the other. So when you say x plus y is less than 1, you need to draw the line x plus y is equals to 1, so that you identify where x plus y is less than 1. So you are basically saying on the xy axis, if you draw on the xy axis, you draw the line x plus y equals 1. This is the line. And usually, basically, this is the same line also I say. This line is also is y equals to 1 minus x. On the xy axis, this line is called y equals to 1 minus x. It's the same line as x plus y equals to 1. So when do you say x plus y is less than 1? In other words, you are saying y is less than 1 minus x. So where y is less than 1 minus x, it should be below the line. And where y is greater than 1 minus x is above the line. So you can say, I want where y is less than 1 minus x, so that x plus y will be less than 1. So it will be the shaded region. So you integrate over the shaded region. This is what will give you the probability. So you can actually see here, you can integrate with respect to x and then y. When you do that, you'll find that the limits of y is 0 to 1, but the limits of x would be from 0 to 1 minus y. You have to express now in terms of y, the limits of x. You see, y will be from 0 to 1, but x will be from 0 to 1 minus y. If you integrate, you will get a half. If you are doing dy dx, will be the other way story. You will find that y will be from 0 to 1. I mean, x will be from 0 to 1, and y will be from 0 to 1 minus x. You'll express y in terms of x when getting the upper limit. And because of symmetry, actually, you can see they look the same. You will still get a half. So you are getting actually the probability that x plus y is less than 1. You are getting that probability. C, look at this. Y less than x over 2. So you need the line y equals to x over 2 on xy axis. This is the line. Then to identify where y is less than x over 2 is below the line. So this is the, and remember, we are doing all these on the unit square. This is where the join is defined. And you can see wherever I'm on the unit square, identifying the region in the unit square. Similarly, you can see I'm still on the unit square, identifying the region on the unit square. So you can actually see here, look at this. If you are saying dy dx, your x will be from 0 to 1, but your y will be from 0 to x over 2. You can see the limits now. And if you integrate, you'll get a quarter. You can see if it was the other way around. If it was the other way around, if it was dy for y will be from 0 to a half. Okay. If you are dealing with dx, dy, y will be from 0 to a half. It cannot go beyond a half. But for x, the upper limit is 1, but x is starting from 2y. So you can see the limits now change. When you are saying dy dx, these are the limits. When you are saying dx dy, you see the limits. You don't just swap unless they are constants like here. Here, it doesn't matter whether you say it dx dy, you can swap the limits because they don't depend on each other. Dx dy
dy dx doesn't matter. But here there is a catch. Hmm? You can see the limits. When you are dy dx 0 to 1, 0 to x over 2. When you are dx dy 0 to a half, 2y to 1. When you simplify, you get a quarter. You simplify, you get a quarter. So it doesn't matter which one you use. You get a quarter. Uh, Look at this E, probability that X is greater than a third. This looks like marginal. But remember, you can use now in the joint, we are saying Y takes possible values. So that means Y will lie over the interval 0, 1. So you can actually see for X will be greater than a third. So a third to 1, and then Y will just be from 0 to 1 because it's not constrained. So for this one, doesn't matter whether you say dy dx, you can even swap. You can say 0 to 1, a third to 1, dx dy. It's the same story. You can swap, doesn't, because they are constants. Because they are constants, doesn't depend, you'll get 2/3. This is the area of the shaded region. F, what's probability that x equals to y? Probability that x equals to y is 0. The way you were saying, when you are dealing with continuous, probability that x equals to x is 0. When both x and y are continuous, probably that they are equal, it will be 0. Because why were we saying it is 0 when you are dealing with bifurcate? Because there was no interval. Why are we saying it is 0 here when you are doing it by bifurcate? There is no region. You see, x equals to y is the line, y equals to x. There is no region. So that they are equal will just be 0. No region. It's like an impossible event. In this remark, why I was bringing this example so that you can see this when you are dealing with probability, in some instances there are physical meanings. In fact, if you look at the unit square, you can see if you integrate the joint over the unit square, you are getting 1. And because the function is actually 1, what really when the function is 1, the probabilities you are getting are actually the areas of those regions. This is what happens in probability in general. When the function is equals to 1, you will find that what you are actually getting is the area of the regions. That is why why we are finding that's a BDF over the unit square. The area of the unit square is 1. It is actually giving you the area. If you see in B, what you are getting as a quarter will also be the area of the region in question. And you can say this will be a quarter because it says, it is 0 to 1, 0 to 1, and then you are saying 0 to a half, and then 0 to a half. We are taking actually a quarter. It's actually a quarter. That region will define a quarter. 0 to a half, 0 to a half is a quarter. A quarter of the entire region. So you're actually saying length a half, length a half. The length is a half, the height is a half. A half times a half, you get, the area is a quarter.
I believe I'm back now.
Yes, you are.
Thank you very much for the intervention. And I was actually having a recap. Not really, I was winding up. So what I was stressing here was the physical meaning when the function is 1. Usually it gives you the area of the support. So it has got a physical meaning. This is the area, the way we know what an area is. And this example demonstrates that. You look at the area of those shaded regions, those are actually the physical meaning, they are the areas. So a probability, in cases where it is not 1, it may not have that physical interpretation, which is tangible, but now talks about just the chance of occurrence of whatever nature, depending on the function. So you can always find the reason why I was stressing about this FYD0 is that when you are dealing with continuous random factor, when there is no region, the probability is zero. So that's why I was putting this F to illustrate that no region. You're having the line y equals to x, there is no region as such. You know. So I was saying in this remark, if f of x to y equals to 1, the probability over a given region is the area of that region. The region in question being defined is the area of that region. So it has a physical meaning. So I didn't want to stop without telling you that there's an exercise here. You have the chain BDF. This is basically a rect. This is basically 0 to 3 equals a square. The support is the square. 0 to 2, 2 to 4 is a square of some form. And the probabilities are given by that function. First, verified is a BDF. Integrate over that square. But remember, yes, x lies between 0 and 2, but y lies between 2 and 4. Still a square. Verify that is a BDF, so integrate and show it is 1. And then we find this probability. So you'll find this probability. This one now will not give you the area because the function is not 1. It will just give you some probability. There's no physical interpretation like area. And then in B, I've said show that. So you must identify the region. The line of interest here is y equals to x plus 2. Identify the region where y is less than x plus 2. You integrate over that region, the function. You'll get the probability. Similarly here, x plus y is less than 3. The line of interest is y equals to 3 minus x. Identify where x plus y is less than 3, or basically where y is less than 3 minus x. Simplify that. You have to identify the region. Get the limits appropriately, the way we have been doing up there. Get the limits appropriately. So these are show. So you'll find this in this B, you note when you are doing dx dy or dy dx, you don't just swap the integrals. But you'll find that you can actually do with this because they are constant. They don't depend on each other. X less than 1, y less than 3, doesn't matter. You can just swap the integrals. But this one, you don't just swap. The limits will change because you'll find that the limits of one random variable depends on the other random variable. Of course, the values of the other random variable. 2, x and y have the chain BDF. Again, verify that f of xy is a BDF. Why I brought this example is that you can see the support. The support, it says 0 less than x, x less than y less than 1. It is not the unit square. You must identify the support first. The function is actually 2 over that support. But it's not the if you integrate this over the unit square, you will not get 1 because it's not the support is not the unit square. You have to look for the line y equals to x, and this one is defined where y is greater than x or where x is greater than y. Draw it and can even shade it, and then you know. And then you look for the limits appropriately, whether you are saying dx dy or dy dx. The limits also, you don't just swap. Verify that it is a BDF. That means if you integrate over the support, you should get 1. And then B, find this probability. Probability that 2y is less than x plus 1. So you must identify the region, get the limits appropriately, and then integrate to find that probability. And if you check in this exercise, you find that in 1 and also in 2, the functions are not equals to 1. So we cannot interpret those probabilities as areas, no, in the usual manner, the way what we know the physical meaning of an area. So since our probability function is not one, the probability of a given region is not the area of the region. No, they don't have that physical interpretation as we know as of area. Thank you. That's why I was saying I'm winding up. And my intention was to stop there. At this point in time, you cannot start something new. It will be too much. So you have a number of exercises to do. Please do. Good evening.